So mentioned the Schrodinger equation and how the solutions are these wave functions. The wave function squared gives us the probability density, which would be the probability divided by a unit volume. For the s orbital, it's spherical, so that's kind of convenient, s for sphere. That's not why it's s, but it works. So we see that the probability density decreases as the distance increases from the nucleus, meaning the further you get away from the nucleus, the less likely you are to see an electron. And so we can plot this, and it looks a lot like a multiple exposure photograph. Like you've got a camera set up, and the shutter clicks, and maybe you've got a moth, and it clicks, and you see the moth is here, and then the next time it clicks, the moth is over there, right? What's important here is that even though it looks like that, the electron is not moving around the nucleus like a moth around the flame. In a sense, the electron's location is spread out over the entire orbital. In fact, what it's really like is a standing wave. So this would be the plot, and I don't know what I did there. And this would be probability density versus R. So there's a problem with this, because this shows the highest density at the nucleus, but the nucleus is the place where the electron cannot be. So this is not quite right. We're going to throw in a radial distribution function. I don't even see the point in saying all those words. There they are. You can read them if you want. What that does is it gives us a plot like this, where the probability of being at the nucleus is 0, and it increases as we go out. There's a maximum, and then it decreases, and so you're probably going to find the electron between 0 and 200 picometers from the nucleus of the hydrogen atom. So the most likely distance is the 52.9 picometers, and that actually corresponds to the radius that Bohr came up with, predicting the radius of that first energy level. There's an important conceptual difference here. Bohr said that the electron is always at 52.9, almost like it's on a string, right? Like the Earth has a constant distance, relatively, from the sun, right? That's not what the electron does, although it's convenient to think of it. It's easier. Quantum mechanics says the electron is found at a lot of different radii, but 52.9 is the most common, the most probable. So if you take a piece of rope or a piece of string and you hold it still at both ends, and then you vibrate it so that you make a wave, if you vibrate it at just the right frequencies, you can get standing waves to happen on the string. And so this string is actually going up and down and up and down, but it kind of blurs together, and it almost looks like this is a solid shape. This is what's called a node, where the string is not moving, where the wave is coming up and down and up and down and back to the middle. So a node is where there's 0 probability of finding an electron. So this would be like at the nucleus, and this would be a first node and a second node and a third node. When you get into those higher energy levels, 2s and 3s, those are also spherical, but they're bigger, and now they have nodes in them. A node is a point where the wave function goes through 0. So the probability of finding an electron at a node is 0. So if we look at a cross-section of a 2s orbital, there's this standing wave part in here, and then there's a node, and then there's more probability density here. And the 3s has 2 nodes. So it could be in here, or it could be in here, or out there. And actually what it is it's in all of those places. So if you think about this, this is a bit like an orbital. Where is that wave? Well, it's occupying all that space, right? But if you took a picture of it and froze it at an instant in time, you'd see that it's in a particular place. So the electron is like a standing wave, and if you try to identify where it is, you're taking a picture, then you can see where it is, but you can't see its velocity or anything like that. So if you took a picture of this string moving up and down, you might see, well, one time it's here, another time it's there, but you would see that you'd never see the string up here, right? Because it's not moving there. So every principal energy level has an L equals 1 sublevel, an S orbital, and those are going to be spherical. Those will always be the lowest energy. And then starting with N equals 1, you can also have a P sublevel, and these look like this. So this is more of the multiple exposure, and this is easier to draw. It's important to understand that the p orbital is not a balloon shape that contains the electron, okay? This is just a region where you're probably going to find the electron. The edges are actually fuzzy. The electron will never be in the middle, but the electron is on this side and on that side at the same time. What? Well, if you think about this as being like that standing wave on the string, the wave was here, and the wave was here, but not in the middle. The electron, if you take a picture of it, force it to behave like a particle, it has to be on one side or the other. But if you're not forcing it to act like a particle, it can behave like a wave, and it can be on both sides without going through the middle. It is disturbing. Any questions? And the next one, L equals 2. These get even weirder. Looks like we're doing some very strange balloon art, doesn't it? So the d orbitals, there's 5 different ones, and instead of having 2 lobes, most of these have 4 lobes. And this one's arranged on the YZ plane. This one's in the XY plane, the XZ plane. This is in the X squared, Y squared plane. And then there's this freaky one that's like a dumbbell wearing a life preserver. And then there's the F orbitals. Nice. Those are really weird. There's 7 of them. I will never make you draw those. But look, you've seen them. I showed them to you. So these orbitals are mathematical wave functions. So they really are waves. Wave functions can have positive or negative values. It can also have nodes where the wave function is equal to 0. So if the sign of the wave function is positive, that's a positive phase, or it can be in a negative phase. When orbitals interact, their wave functions might be in phase with each other or out of phase with each other. And this is really important for some bonding concepts we'll talk about later, but this again relates to constructive and destructive interference between waves. So for the s orbital, the 1s orbital doesn't have a node, and so here we see it in a positive phase. The p orbital has a node in the middle, and so one side is positive and the other is negative phase. And so if these things overlap, they can reinforce each other or they can cancel each other out. So we saw all those crazy balloon shapes, right? So why do we always show atoms as being spheres? Well, if you take all of those crazy shapes and superimpose them on top of each other, right, you're going to get something like this, which is very close to spherical. So we've got all these different possibilities going on in there. And so, I mean, I just think of the electrons, they're doing crazy things, right? Described by these wave functions, but just, they're very squirrely. You can't get your finger on them. It's okay to not understand what the electrons are doing.